Orbiting the magnificent ringed planet Saturn in the vastness of our cosmic neighborhood is a world of striking differences and scientific enigmas. Dione, named for the Greek mythological Titaness, has a bright, reflective surface that conceals old wounds and geological marvels. Out of the more than 200 known systems, it is the fourth largest. Spacecraft. Its diameter is only 1,120 km, which is less than the width of Texas. However, despite its small size, this frozen world has secrets that remain fascinating to both astronomers and planetary scientists. The day we travel to this far-off moon, a location where icy cliffs rise above craters' valleys, where the surface is streaked with enigmatic, wispy terrains. Additionally, where this world is unlike any other because of orbital resonance forces. This is Dione, Saturn's broken moon. Similar to numerous moons of Saturn, Dion's in the early days of telescopic astronomy, discoveries were made. The famous Italian was the first to notice it. Astronomer Giovanni Cassini on March 21st, 1684. 2 years prior, Cassini had already found Saturn's moon Iapetus while working at the Paris Observatory. Would later find Rhea and Tethys, 2 additional moons of Saturn. At first, Cassini just referred to it as Saturn IV, indicating that it was Saturn's fourth moon in terms of distance. It wasn't until 1847 that English astronomer John Herschel proposed giving Saturn's moons the names of Greek mythological titans, which is how Dione got its mythological term. The name is appropriate. Dione was a titaness in Greek mythology, frequently described as Oianis and Tethys' daughter, and occasionally regarded as one of Zeus's consorts. She may even have been Aphrodite's mother, according to some myths. The moon Dione, like its mythological namesake, would later reveal unexpected ties and relationships to other. It was reduced to little more than a point of light in our telescopes, centuries after it was discovered, a perplexing world that we knew very little about. Even with the strongest power on Earth, few of the secrets of this far-off moon were discovered by observatories. Each of these would change dramatically with the dawn of the space age. Our first clothes would undergo a significant transformation as the space age began. Our initial clothes, NASA's Voyager 1 spacecraft, which passed by the Saturnian system in November 1980, provided a glimpse of Dione.E Saturnian system in November 1980. Dione only started to change from a dot of light as Voyager got closer, into a world with unique characteristics and personality. However, the Voyager photos revealed a moon with a complicated surface, limited by the technology available at the time. Dione appeared heavily cratered on its trailing hemisphere, the side that faces away from its direction of orbit. On its trailing hemisphere, the side that faces away from its orbital direction, Dione appeared to be heavily cratered. Wattiander, a basin about 350 kilometers in size, is the biggest of these impact craters. Dimensions. Other notable craters are Dido and Enas, which are named after other significant craters include Enas and Dido, named after parts of its surface were crisscrossed by bright streaks. These characteristics, which scientists named wispy terrain, looked unlike anything found on other bright streaks that crisscrossed portions of its surface. These characteristics, which scientists named wispy terrain, looked unlike anything found on other worlds back then. However, Voyager's limited flyby and imaging capabilities could only pique our curiosity about understanding of this mysterious moon. Dion's diameter, as determined by the spacecraft, was approximately 1,120 km, making it Saturn's after Iapetus, Rhea, and Titan. It is the fourth largest moon. Additionally, Voyager discovered that Dione's density of roughly 1.48 Dre per cubic centimeter indicates a composition mostly composed of water ice with a small amount of rock, probably with a tiny silicate core. However, planetary scientists had more questions than answers after the brief encounter. Which were those enigmatic wisps? How did the surface of Dione change? What factors influenced this far-off world? Another spacecraft named after Dion's Italian discoverer would be required, from 400 years ago to actually start solving these puzzles. NASA's Cassini spacecraft began orbiting Saturn in July 2004. What would turn out to be a 13-year exploration mission across the Saturnian system. This advanced spacecraft carried a collection of scientific tools that would transform our knowledge of Saturn and its moons. Additionally, during its mission, Cassini made multiple close flybys of Dione, getting as close as 99 kilometers to the moon's outward. These interactions produced previously unheard of high-resolution photos and an abundance of scientific information about this enigmatic world. Cassini made one of the most important discoveries when he revealed the actual characteristics of the enigmatic, hazy landscape that Voyager first saw, which had from a distance appeared as bright, streaky deposits were actually exposed. Cliffs of ice, the faces of massive faults piercing the icy crust of Dione. They, in certain instances, what are now known as chasmata, are hundreds of kilometers long and several kilometers below the surface. Palatine chasmata is the most noticeable of these characteristics. Enormous fracture system that spans Dione's surface for more than 600 kilometers. Carthage fossae and Padua chasmata are two more significant fracture systems. Within these fissures, cut through craters and other surface features in some places, suggesting that they formed relatively recently in the geological past of Dione. Dione's measurements of density from the Cassini mission verified that it is mostly made of water ice with a sizable rock component, about 40%. 60% of the mass is made up of ice and rock. This gives Dione a mass of about 1.1. 10. Agul Nasukaung. Scientists confirm that Dione most likely has a differentiated interior based on this density and mass, with a thick layer of ice encircling a modest, rocky core. The exterior Dione's average temperature is a scorching 187 degrees. In those, because water ice behaves like rock on Earth at different temperatures, solid geological features can form, such as canyons, mountains, and craters. As previously stated, half of Dione's surface is dotted with craters, evidence of past collisions. However, perhaps more fascinating, the regions where craters are noticeably lacking are those with craters. There is evidence of resurfacing in some areas of Dione. Older features have been erased by geological processes that have produced smoother aircraft. These regions, which are mostly on the leading hemisphere, indicate that Dione has gone through times of internal activity that have revitalized some of it to the nearby older surface material that has been darkened by radiation and micrometeorite exposure effects spanning billions of years. However, what led to these massive fractures? According to the predominant theory, they developed as a result of global stress patterns in the icy crust of Dione. Dione cooled, and its crust would have undergone tension and compression forces as it developed over billions of years, ultimately leading toto-breaking. These fractures, according to some scientists, might indicate that Dione once had an ocean beneath the surface that eventually froze. When water freezes, it expands. The outer crust would have been under tremendous stress from ice growth, possibly leading to the patterns we observe today. Others propose that the stretching and squeezing of tidal flexing Dione may have produced enough heat and stress to produce these features because of Saturn's gravitational pull, impacts over billions of years. But what caused these enormous fractures? The leading theory is that they formed in response to global stress patterns in Dione's icy crust. As Dione cooled and evolved over billions of years, its crust would have experienced tension and compression forces that ultimately led to fracturing. Some scientists believe these fractures may be evidence that Dione once had an ocean that eventually froze beneath the surface. Water expands when it freezes. The outer crust would have been under tremendous stress from ice growth, possibly leading to the patterns we see today. Others suggest that tidal flexing, the stretching and squeezing of Dione due to Saturn's gravitational pull, may have generated enough heat and stress to create these features. We still lack complete answers. At a distance of roughly 374 km, Dione completes one orbit of Saturn every 2.7 Earth orbits a day. Because Dione is neatly locked to Saturn, the same side is constantly facing the planet, in the same way that Earth always sees the same face of our moon. Similar to numerous moons, Dione takes part in a worldwide dance of orbital resonances in the Saturnian system that has significant consequences for its development. The 21 mean motion is arguably the most important of these relationships. Resonance that Enceladus alone possesses. Resonance that Enceladus alone possesses. Thus, for each orbit, Dione Enceladus completes precisely 2 orbits around Saturn. Enceladus completes precisely 2 orbits around Saturn. That's not just a coincidence. Not just a coincidence. These 2 moons are trapped in a gravitational relationship. Synchronized pattern that has an impact on both worlds. Tidal forces are produced by this resonance. Tidal forces are produced by this resonance that produce heat on both moons. On Enceladus, however, the effects are far more pronounced. Indicating remarkable geological activity, such as its well-known southern polar geysers that constantly erupt water ice into the void. Due to its size, Dione experiences proportionately less tidal heat from this partnership. Did you also know that Dione has a tiny spacecraft? Helena and Polluces are 2 small moons. Orbit the same distance from Saturn as Dione. These moons are located in what is known Lagrange points in the orbit of Dione. Stable gravitational locations that come before and track Dione's orbit around Saturn. Sometimes referred to as Trojan, these tiny moons, which are only a few kilometers in diameter, were probably formed or captured from debris in the vicinity of Dione's orbit. Moons, which are only a few kilometers in diameter, were probably formed or captured from debris in the vicinity of Dione's orbit. However, what about that ocean beneath the surface? The prospect is undoubtedly fascinating. Any such place in the solar system always fascinates scientists because of the potential for all oceans to be the place where life is born. Therefore, the presence of an ocean would be important on Dione, but it isn't without proof. Dione and Saturn's weak interaction was observed by Cassini's magnetometer. Magnetosphere, which some researchers believe provides proof of a conductive layer beneath the surface, perhaps an ocean below the surface that is salty. Additionally, the extensive fracture systems on the surface of Dione indicate that there was substantial geological activity there in the past, which might have been fueled by liquid water. Lower. Dione's internal heat budget models that take radioactive decay into account in its tidal heating from its orbital resonance with Enceladus and its rocky core indicate that it might have produced enough heat to keep a liquid layer between its icy crust and core throughout its history. If Dione has a subsurface ocean, it would become one of our solar system's increasing number of ocean worlds. Locations such as Europa, Enceladus, and possibly Titan, which might offer habitable settings for basic life forms. But in contrast to Enceladus, which has its Dione, does not currently exhibit any indications of the dramatic plumes of water vapor erupting into space, of geological activity that would make any subterranean ocean easily accessible. If Dione has an ocean, beneath kilometers of ice, it is still well hidden. Since the Cassini mission's conclusion and since the spacecraft was purposefully dropped into Saturn's atmosphere in 2017, no other spacecraft has traveled to the Saturnian system. Thus, our present comprehension of Dione is solely on the information gathered from these brief interactions with Cassini and Voyager. But the scientific community has put forth a number of ideas for upcoming missions to the Saturn system, including additional investigation of Dione. These include landers and orbiter missions that would investigate several of Saturn's moons. That might land on Dion's surface, as well as specialized missions to look for indications of an ocean below the surface. The Enceladus orbiter is a particularly ambitious idea that would primarily study Enceladus, but might also fly by Dione several times. The journey to Enceladus and Titan, another proposal, would similarly observe Saturn's other major moons while concentrating on those two. Satellites, such as Dione. Although none of these mission ideas have been given the go-ahead to be developed, the scientific issues brought up by our scant research on Dione guarantee that it will always be a desirable target for upcoming research. After closely examining Dione, we are left with a picture of an intriguing world. Opposites. A moon's seemingly motionless icy surface reveals a dynamic of the past. Its surface is crisscrossed by vast networks of bright fractures that indicate strong forces that have shaped and changed this world over time. The notable distinction between its cratered trailing hemisphere and a smoother leading face insert are continuous processes that to mold its characteristics and minute hints in its magnetic and gravitational signatures hint at a potential ocean beneath its icy exterior. The only one, in many respects, is a prime example of the unexpected complexity we found throughout Saturn's moon system. Through our telescopes, what were once only points of light have become distinct worlds with their own evolutionary histories and geological features. These findings force us to reconsider how we perceive what propels geological activity in the outer solar system, where solar heat is too far away to power the processes we observe on Earth. Dione contributes to the enormous symphony of Saturn's moons. Unique melody, one that keeps captivating us and motivating us to delve further into the secrets of our solar system. Can a moon disappear? As it happens, it is feasible. Early in the history of Iapetus, the Saturnian moon frequently seemed to disappear from view in astronomy. Completely. It was present on some days and absent on others. This was the final magician's trick. However, once we discovered how to do it, Iapetus's mysteries only deepened. This is due to the stark contrast found in Iapetus. Half of it descended into almost complete darkness, with the other half shining with the reflective ice's brightness. A massive mountain range encircling its equator, a stony girdle that is precisely encircling its equator, and whose origins are unknown justification. Why does this moon exhibit such a striking duality? What catastrophic occurrence or gradual, unstoppable process could have shaped a mountain range that is higher than Mount Everest in an inexplicable location? What mysteries does this far-off world conceal about our turbulent youth? Cosmic system, you are viewing me, Alex Mccoan. Strong. Come along with me as we travel to the third largest moon of Saturn, Iapetus, and perhaps its most mysterious. Giovanni Domenico Cassini's astute observation is where our story starts. In 1671, utilizing Cassini discovered a new point using the Paris Observatory's refracting telescopes, of light circling the giant with rings. However, this new moon exhibited peculiar behavior, when there was fairly visible because it was in Saturn's orbit on its western side. However, as it appeared to disappear as it moved to the eastern side, becoming extraordinarily dim, often disappearing entirely from view in those telescopes. Reflecting on in his observations, Cassini observed that sometimes, after beginning to disappear with the 32-foot telescope, it has been sought in vain the next day with one of 45. Cassini came to the conclusion that this moon must have one hemisphere that is noticeably darker than the other, and like our own moon, it must be neatly locked to Saturn, maintaining the same face toward its planet at all times, toward the planet Earth. This meant that Iapetus alternates in its orbit around Saturn, showcasing both its dark and bright faces to Earth, when the positive "it" was visible from our vantage point, facing us on the western side of its orbit. When the shadowy side confronted us, it disappeared from view on the eastern side. It was a startling discovery for the planetary moon that is not part of the Earth-Moon system. The 4 moons Cassini found were named Sidera Lossier, or the Star of Louis in remembrance of King Louis XIV. However, these names did not endure. Afterwards, John Herschel proposed names derived from the mythological Titans, who are Saturn's siblings. As the father of Atlas and Prometheus, Iapetus is also the father of this strange world, was named after Prometheus's creations, mankind. Iapetus was little more than a point of light displaying this strange variation in brightness for centuries. Even so, in the late 1970s and early 1980s, the Voyager probes transformed our knowledge of the outer solar system. Only accomplished far-off flybys in the 1980s. Voyager 1 took pictures demonstrating that Cassini's deduction was confirmed by the dark brightness difference, but the resolution was insufficient to show the complex details. Voyager 2 performed marginally better, getting closer and providing us with our first enticing look at yet another incredible feature. An indication of the enormous ridge close to the equator. However, the complete image, the stunning Iapetus's peculiarities, would have to wait until a dedicated Saturn-arrived investigator. The Cassini spacecraft, named appropriately after the person who discovered the moon. When the Cassini reached Saturn in 2004, the ring planet and its varied family of moons would be the subject of a 13-year mission, and Iapetus was high on its list of objectives. Cassini's findings, especially a September 2007, saw a close, targeted flyby that brought the probe within 1,240 kilometers of Iapetus's surface, changed the moon from a far-off glint into a complex world that we could at last learn about. The moon Iapetus has a low density, only 1.2 times the density of water, indicating that it is made up of up-to-water ice, 75%. Its imperfect spherical shape is partly caused by the equatorial ridge, resulting in its characteristic oblate walnut-like seeming. It probably doesn't have a subterranean ocean like Enceladus or Europa, since there is no proof of recent tidal heating or geological activity required to keep liquid water under its icy shell. The surface of it is old, frigid, and severely cratered, especially in the bright areas of Terra, bearing witness to bombardment spanning billions of years. Its orbit is also peculiar. Compared to other Saturnian planets, Iapetus has a much farther orbit. Moons that are roughly 3.5 million kilometers away on average, over twice the distance to Titan, the next major moon. Because of the distance, it takes 79.31 orbit around Saturn takes Earth days. Importantly, its orbit is also slightly slanted, with a 15-degree tilt with respect to Saturn's equatorial plane, where the majority of other large moons revolve. Iapetus is less impacted because of this distance, by the strong radiation belts nearer Saturn and the planet's magnetosphere. The inclination of its orbit could be a hint about its early migration history or formation, perhaps suggesting that it didn't form with the same equatorial disk as the regular moons that are closer to Saturn. However, let's move on to the Iapetus aspect. That gives it such a captivating appearance. Its exterior is clearly separated into 2 different areas. The frontal hemisphere, the Iapetus's forward-facing side, is extremely dark as it circles Saturn. This area is approximately 40% of Iapetus's surface and is referred to as Cassini Regio. It's the amount of light it reflects, or albedo, is incredibly low, somewhere from 0.03 to 0.05. That is as dark as coal dust or asphalt. Nearly all of the light that strikes it is absorbed by it. Conversely, the trailing along with the poles, the hemisphere, the side that faces away from the direction of orbit, is extremely bright. This area includes Saraosa Terra to the south and Ronvu Terra to the north, an albedo of 0.5 to 0.6, 6 times brighter than recently fallen snow or brilliant ice made of water. The biggest interseismic difference is this nearly 3-fold difference in albedo. Albedo contrast in the solar system that we are aware of. Just picture this world. Close up. One side is a brilliant white, while the other is a deep reddish brown or black. Within, in some places, especially close to the equator, the line dividing those two halves can appear remarkably sharp, as if it is painted on. In other regions, particularly those with higher latitudes, with bright raid craters strewn across the dark, the transition is more gradual. Terrain and dark patches that resemble mud, splashes on the bright terrain frost. This contrast is clearly depicted in this Cassini image. It's a world, literally divided in half. What is the reason behind this appearance of yin-yang? For a considerable amount of time, the dominant theory suggested an internal source, maybe a dark cryogenic substance emerging from the interior of Iapetus, covering one side. An article examining the Bradford Smith and his colleagues' 1981 Voyager data supported this theory, recognizing this ring shape as a partially darkened crater eruptive material as proof. But Cassini's radar and the dark material forms a relatively thin layer, according to imaging data. In most places, it might only be a few centimeters to a meter thick. Additionally, impact bright icy material is frequently excavated from craters in Cassini Regio, punching through the dark veneer beneath. This strongly implied the dark stuff was being deposited from above rather than welling up from below. Spectrophotometric observations of the dark leading surface were reported in a 1982 paper, and discovered that the material's composition was carbonaceous. Like the Murchison C2 meteorite, which struck Earth during a 1969 shower. The authors looked to possible offenders nearby to explain this finding. Iapetus in the system of Saturn. Dust from Saturn's outer atmosphere is the main suspect. Phoebe is an erratic moon. Phoebe is a comparatively big, dark moon, trapped by Saturn's gravitational pull, traveling in the incorrect orbit around the planet. A retrograde orbit at a considerable distance. Over billions of years, effects on due to Phoebe and other tiny, dark, retrograde moons, a huge, precarious ring of particles of dark dust. These dust particles are under pressure from the sun's radiation, particles that are responsible for the Poynting-Robertson effect. Consequently, this dust moves retrogradely as it spirals inward toward Saturn. Orientation. Iapetus. Let us now return our attention to Iapetus. This moon travels around Saturn in a prograde orbit, moving in the same direction as the planet's own rotation and the majority of its other moons. Yet its path is situated significantly farther out than the main ring system and the inner satellites. As Iapetus journeys through its orbit, its leading hemisphere effectively crashes head-on into an incoming stream of retrograde dark particles, which originate primarily from the Phoebe ring group. The phenomenon can be likened to driving a vehicle through a dense swarm of insects. They inevitably splatter predominantly across the front windshield. Consequently, the trailing hemisphere, being shielded by the moon's own bulk, accumulates far less of this obscuring dark material. However, mere deposition of dust does not fully account for the extreme intensity of the blackness observed on the leading side of Iapetus, nor does it explain the intricate complexity of the boundary separating the dark terrain from the bright. It is here that the mechanisms of thermal segregation and water-ice sublimation become critical factors. The dark material that is settled on the leading hemisphere absorbs significantly more sunlight than the surrounding reflective bright ice. This absorption causes the surface temperature to increase slightly. While Iapetus remains incredibly cold, even this minor elevation in temperature is sufficient to trigger the sublimation of volatile water ice, causing it to transition directly from a solid state into water vapor gas. Because Iapetus rotates exceedingly slowly, This sublimating water vapor does not simply vanish instantly. The moon's day lasts approximately 79 Earth days, which is identical to its orbital period. Consequently, daytime temperatures remain elevated for long durations, granting the ice ample time to sublime away from the warmer, darkened regions. Indeed, the rate of sublimation on Iapetus is so rapid that if its surface consisted of pure ice, we would witness the loss of over 100 meters of ice due to sublimation over the course of 1 billion years. This rate is faster than that of any other Saturnian satellite. But where does this migrating ice ultimately go? It preferentially recondenses and freezes onto the colder surfaces available. These locations are the regions that are already bright and icy on the trailing hemisphere and near the poles, which naturally reflect more sunlight and thus remain cooler. Scientists propose that, due to the moon's negligible atmosphere, the sublimating molecules follow ballistic trajectories, leaping impressive distances to the trailing hemisphere much like a missile. This dynamic creates a runaway positive feedback loop, often described as thermal runaway. Dark areas become slightly warmer, lose their surface ice, and consequently become even darker as the underlying dark dust concentrates. Being darker, they absorb even more heat, leading to further ice sublimation. Conversely, bright areas remain cold, acting as traps for the migrating frost. They become even brighter, reflect more sunlight, stay colder, and thus collect even more frost. Over the course of millions and billions of years, this process has dramatically sharpened the boundary between the coal-black leading hemisphere and the snow-white trailing hemisphere, resulting in the extreme contrast we observe today. Thus, the Great Dichotomy appears to be a result of external pollution from retrograde moons combined with an internal sorting mechanism driven by sunlight and sublimation. A truly remarkable example of planetary processes in action. Yet, this two-tone coloration is merely one aspect of Iapetus' strangeness. As the Voyager 2 mission hinted, and as Cassini later confirmed in stunning detail, Iapetus possesses another feature unique within the known solar system, a colossal equatorial ridge. This ridge is effectively a continuous wall of mountains stretching for approximately 1,600 kilometers, spanning at least halfway around the moon's circumference. On average, this structure is about 200 kilometers wide at its base and reaches towering heights of up to 20 kilometers above the surrounding terrain. To put that in perspective, that is significantly taller than Mount Everest. The most baffling aspect is that it follows the equator almost perfectly, primarily confined within the dark region known as Cassini-Huygens. Although additional equatorial mountains identified by Voyager on the trailing hemisphere could well be a continuation of this same structure. In images captured by Cassini during its close flyby, the sheer scale is breathtaking, giving Iapetus a distinct appearance often compared to a walnut. What could have possibly created this belt of mountains? This remains one of the greatest ongoing mysteries surrounding Iapetus. Several hypotheses have been proposed, each presenting its own strengths and weaknesses. One leading theory suggests that the ridge is a relic from a time when the moon spun much faster. Recent models indicate that early in its history, shortly after its formation, Iapetus might have been rotating rapidly, perhaps completing a rotation in around 16 hours. This rapid spin would have increased its oblateness, causing the equatorial regions to bulge outward due to centrifugal force, while the moon was still young and relatively plastic or partially molten. As Iapetus cooled and solidified, this equatorial bulge effectively froze in place. Later, gravitational interactions with Saturn slowed the moon's rotation over millions of years, until it became tidally locked, rotating only once per 79-day orbit. As it slowed, the centrifugal force supporting the bulge diminished, and the now solid crust could not fully relax back into a sphere. The material essentially slumped downwards, piling up near the equator to form the massive ridge we see today. This theory aligns well with the ridge's precise equatorial location and its ancient, heavily cratered appearance, suggesting it formed very early on. However, it requires Iapetus to have spun incredibly fast, possibly close to its structural breakup speed, and to have solidified while maintaining that extreme bulge. Another intriguing hypothesis proposes that the ridge is the result of material falling onto Iapetus from an external source, specifically the collapse of a sub-satellite or a ring system that once orbited the moon itself. If Iapetus possessed a debris ring early in its history, perhaps sourced from a captured body or a large impact, this material would naturally orbit above its equator. If this ring became unstable, or if Iapetus migrated slightly in its orbit, the ring material may have been pushed just beyond the Roche limit, the point at which the tidal effects of a large body overwhelm the internal gravity of a smaller one. This may have caused the ring material to slowly rain down onto the surface of Iapetus, piling up preferentially along the equator. This could potentially explain why the ridge seems most prominent on the dark leading hemisphere, if the ring material itself was dark, or if its deposition coincided with the influx of dark dust from Phoebe. Some models suggest that even a small moonlet breaking up within Iapetus's Roche limit could provide enough material. While elegant in explaining the location, the exact mechanisms for forming and then collapsing such a ring are still matters of debate. Other theories, such as tectonic processes or convective upwelling from the interior, struggle to explain why the activity would be so narrowly confined to the equator over such a vast distance. Similarly, a giant impact is unlikely to produce a long, linear, and perfectly equatorial feature. Cassini's detailed images show the ridge is heavily cratered, confirming its ancient origins. It appears to be structurally composed of icy crustal material, and some sections show evidence of landslides and collapse features. Whatever the process, it must have occurred very early in Iapetus's history, perhaps within the first few 100 million years of the solar system's formation. The ridge stands as a monumental memento of Iapetus's dynamic youth, a frozen record of processes we are still striving to understand. So, what do we really know about Iapetus? We know more than we used to, but certainly less than we would like. The Cassini mission fundamentally changed our perception of this fascinating moon. Its close flyby provided the data that solidified the exogenic dust and sublimation theory for the planet's two distinct faces. It gave us astonishing high-resolution views of the equatorial ridge, allowing for detailed study of its structure and morphology, even if its ultimate origin remains debated. Cassini measured Iapetus's shape, gravity field, and surface composition with unprecedented accuracy. Without Cassini, Iapetus would have largely remained the faint, perplexing point of light it was for centuries. And yet, there are still so many mysteries. What is the true origin of the ridge? What is the dark material on the mysterious face actually composed of, beyond simply being carbonaceous? Unless we return there, it will be difficult to know for sure. No missions are currently planned to sample or even circle this perplexing place. So for now, we remain in the dark, which feels somewhat appropriate. After all, as noted at the beginning, Iapetus was once the ultimate vanishing act, and a magician never reveals all his secrets. Rhea. In the vast expanse of our solar system, orbiting the ringed giant Saturn, lies a world defined by ice and mystery. This is Rhea, Saturn's second largest moon. Although you are more likely to have heard of its largest sibling, Titan, Rhea is a fascinating place in its own right and harbours many secrets and wonders. It possesses ice cliffs hundreds of meters high, an internal structure that defies standard scientific models, and an enigmatic discovery that lingers around this moon, one that is equally as strange as the things we failed to find. It is time for this lesser-known moon to step out from its larger sibling's shadow. Let us learn all there is to know about Rhea. Rhea was discovered on the 23rd of December, 1672, by Giovanni Domenico Cassini, the Italian astronomer who made numerous contributions to our understanding of Saturn and its moons. Named after the Titan goddess Rhea in Greek mythology, this moon has been a subject of fascination for astronomers and planetary scientists for centuries. Let us begin with the basics. Rhea is the second largest moon of Saturn after the mammoth Titan, with a diameter of 1,528 kilometers. It is roughly half the size of our own moon. If we were to place Rhea next to Earth, it would stretch approximately from London to Warsaw. Rhea orbits Saturn at a distance of about 527,000 kilometers, completing one orbit every 4.5 Earth days. It is locked in synchronous rotation with Saturn, meaning the same side always faces the planet, a common feature among large moons in our solar system. The surface of Rhea is one of the most reflective in our solar system, boasting an albedo of 0.7. This means it reflects 70% of the sunlight that strikes it, appearing bright white against the black backdrop of space. This high reflectivity is due to its composition. Rhea's surface is primarily made of water ice, but this does not make it a featureless ice sheet. Far from it. The moon is heavily cratered, telling a story of ancient impacts and a long, violent history. The largest of these craters, named Mammoldi, spans an impressive 480 kilometers in diameter, about the distance from Paris to Amsterdam. These craters are not merely scars on Rhea's surface, they are windows into the moon's past and composition. Observations have shown that the bottoms of some craters appear darker than the surrounding terrain. This could indicate that impacts have excavated material from beneath Rhea's bright surface, possibly exposing darker amorphous water ice and impact melt. In various photos, you can see craters in the southern hemisphere of Rhea, surrounded by bright ejecta blankets. One of the most intriguing features of Rhea, however, is its system of bright, wispy streaks that crisscross its surface. These were first observed in detail by the Voyager space probes in the early 1980s, but their true nature wasn't understood until the Cassini mission provided high-resolution images decades later. Initially thought to be deposits of frost or ice ejected from volcanoes, these wisps were revealed to be massive ice cliffs, some standing hundreds of meters high. They are likely the result of tectonic activity in Rhea's past, where the icy crust fractured and some sections were thrust upward. These features give us vital clues about the moon's geological history and the processes that have shaped its surface over billions of years. Rhea's mysteries do not end at its surface. In 2010, data from the Cassini spacecraft led to a surprising announcement. Rhea appeared to have a tenuous atmosphere, or exosphere. A small amount of gas around an icy moon is expected, but it was unexpected that there is enough to be measurable. The detected atmosphere consisted primarily of oxygen and carbon dioxide, with the oxygen being about 5 trillion times less dense than Earth's atmosphere at sea level. While incredibly thin, the mere presence of this atmosphere raised intriguing questions about its origin and sustainability. One theory suggests that the oxygen is produced by the decomposition of water ice on Rhea's surface, when it is struck by energetic ions from Saturn's magnetosphere. The carbon dioxide, on the other hand, is thought to be the result of organic molecules on the surface being oxidized by the oxygen in the exosphere. This discovery made Rhea the first moon known to have an oxygen atmosphere other than Jupiter's moons Ganymede and Europa. It also opened up new avenues for research into the complex interactions between Saturn's moons and the planet's powerful magnetosphere. Rhea's exterior is fascinating, but what about its interior? Let us dive deeper, literally. While we cannot directly observe what lies beneath Rhea's icy surface, scientists have used various methods to infer its internal structure. Based on Rhea's average density of 1.236 grams per cubic centimeter, which is only slightly higher than that of water, we can deduce that Rhea is composed primarily of water ice, about 75%, and a smaller fraction of rock, making up the remaining 25%. Rhea has often been described as a frozen, dirty snowball due to this structure. This puts Rhea in stark contrast to moons like our own moon or Io, which are primarily rocky bodies. When Cassini visited Rhea, the probe's instruments also provided valuable data about Rhea's composition. Spectroscopic observations confirmed that water ice is the dominant component of Rhea's surface, but they also detected the presence of other materials. One surprising discovery was the detection of carbon dioxide trapped in the surface ice. This finding suggests that Rhea's ice isn't pure water, but contains other compounds, possibly including complex organic molecules. Due to its moment of inertia, most scientists believe that Rhea is not differentiated into layers. Instead, it is thought to be a homogeneous mix throughout, with the exception of perhaps a very small core. Some scientists, however, challenge this model. In 2006, a paper was released in the journal Icarus, suggesting that Rhea might have a layer of liquid water under its surface, a subsurface ocean. While this idea is still highly speculative and not as well supported as the subsurface oceans on moons like Europa or Enceladus, it represents an intriguing possibility that future missions might investigate. The presence of such an ocean would have significant implications for Rhea's potential habitability and for our understanding of the conditions necessary for liquid water in the outer solar system. Rhea's interior contains mysteries, but one of the puzzling features of Rhea is its shape. While many large moons and planets tend towards a perfect sphere due to their own gravity, Rhea is noticeably non-spherical. It is slightly flattened at the poles and bulges at the equator, a shape we call a triaxial ellipsoid. What is strange is that Rhea's shape doesn't quite match what we would expect based on its current rotation rate. This discrepancy has led scientists to propose that Rhea might have a non-uniform internal structure, or that it froze in this shape when it was spinning faster in the past. Now, let us discuss one of the most exciting moments in Rhea's recent history: the Cassini mission's close flybys. The Cassini spacecraft, a joint project of NASA, ESA, and the Italian Space Agency, spent over a decade studying the Saturnian system, including several close encounters with Rhea. The closest of these flybys occurred on the 11th of January 2011, with Cassini passing a mere 76 kilometers above Rhea's surface. Another significant close flyby was on the 9th of March 2013, when Cassini passed just 997 kilometers above the surface. This close approach allowed the spacecraft to capture incredibly detailed images of Rhea's cratered terrain, gather valuable data about the moon's composition, and determine that it does not have an internal magnetic field. These flybys provided us with our best look yet at Rhea's surface features. They imaged a landscape dominated by two types of terrain: heavily cratered regions and younger, smoother plains, which were first shown in earlier Voyager missions. The heavily cratered areas are thought to be extremely old, possibly dating back to the early days of the solar system. These ancient surfaces provide a record of the intense bombardment that occurred in the solar system's youth. The smoother plains, on the other hand, are likely the result of a resurfacing event, such as material ejected from large impact events falling back to the surface, filling in older craters and creating smoother regions. But perhaps one of the most intriguing results from the Cassini mission was what it didn't find. Prior to Cassini's arrival, some scientists had proposed that Rhea might have a system of rings. This idea was based on unusual measurements of electron densities around Rhea made by Cassini in 2005, which suggested solid material was blocking the flow of electrons. However, despite careful visual searches during its flybys, Cassini found no evidence of rings around Rhea. This non-detection doesn't completely rule out the possibility of some kind of tenuous debris disk, but it does make the existence of a substantial ring system much less likely. Another intriguing aspect of Rhea is its place in Saturn's complex system of moons. Rhea orbits Saturn in what is known as the E ring, a diffuse ring of ice particles thought to be supplied by the cryovolcanic eruptions from Enceladus. While Rhea itself doesn't seem to be geologically active like Enceladus, its position in this ring means it is constantly interacting with these ice particles. Although Rhea is in the extremities of the E-ring beyond where it is densest, over time, this interaction could affect Rhea's surface properties and contribute to the moon's bright appearance. As we reflect on what we have learned about Rhea, it is clear that this moon, often overshadowed by its more famous siblings, is a fascinating world in its own right. From its heavily cratered hemisphere to its relatively smooth side, From its tenuous oxygen atmosphere to its place in Saturn's complex system of moons, Rhea continues to intrigue scientists and spark our imagination. But our exploration of Rhea is far from over. Many questions remain unanswered. What is the exact nature of its interior structure? How has it evolved over the billions of years since its formation? Could it harbour simple forms of life in a hypothetical subsurface ocean? These questions and more await future missions to the Saturnian system. While there are currently no planned missions specifically targeting Rhea, the moon is likely to be observed by any future spacecraft sent to study Saturn and its moons. Tethys. You might not know much about Tethys, but there is one crucial fact you should grasp. The moon called Tethys is a survivor. It is an icy world orbiting Saturn at a distance of 295,000 kilometers. It may appear unremarkable at first glance, until you learn what it has endured, at which point you might be amazed that it is even here at all. Take a closer look at its scarred surface, and the evidence becomes clear. Not many moons house a gargantuan trench system that wraps around 3/4 of their body. A tectonic rupture so vast, it beggars belief for a world of this size. And directly opposing it, a gigantic impact basin stares back, evidence of a collision so violent it should, by all rights, have blasted this moon into fragments. What caused this? And how did Saturn's 5th largest moon survive the onslaught? The answers lie in its frozen, icy shell, and today, they are coming to light. Tethys' first observation came from Giovanni Domenico Cassini. Following his arrival at the Paris Observatory, Cassini identified Tethys in 1684, alongside Dione, adding them to his count of Saturnian moons that already included Rhea and Iapetus. Following the custom of the time, these were initially dubbed the Sidera Lodoicea, or Stars of Louis, in honor of King Louis XIV, but the name didn't stick. In the 19th century, John Herschel proposed a naming convention drawing on the Greek Titans to tie in with Saturn, Cronus, the Titans' king. Tethys, fittingly for a water ice world, was named after a Titaness and sea goddess, and it is indeed icy. A key characteristic revealed by gravitational measurements, primarily from the Cassini spacecraft, is Tethys' remarkably low density, approximately 0.97 grams per cubic centimeter, or 0.97 times that of liquid water. As a result of this, Tethys' mass is less than 1% of that of our own moon, despite spanning 1/3 of its diameter. This extremely low value strongly indicates that Tethys is composed almost entirely of water ice, with a small amount of rocky material integrated within. It suggests Tethys likely never fully differentiated into a distinct rocky core and icy mantle. Or if it did, the core is exceptionally small. The density might also imply some degree of internal porosity, meaning the ice within might not be perfectly compacted, potentially containing voids or less dense ice structures. This composition makes Tethys a quintessential example of an outer solar system ice world. Physically, Tethys presents as a typically bright, icy satellite. Its high bond albedo, reflecting around 60% of incident radiation from the Sun, confirms a surface dominated by water ice. Relatively free from significant amounts of darker rocky or carbonaceous contaminants seen on moons like Iapetus or Phoebe, Tethys has an irregular shape resulting from the gravitational influences of its neighbours. The classical sphere shape has been squashed into a triaxial ellipsoid, meaning that it has 3 distinct axis dimensions. However, perhaps the most arresting feature on Tethys is one of its landmarks, Ithaca Chasma. This enormous canyon system dominates the moon's topography. It measures up to 2,000 kilometers long, 100 kilometers wide, and 5 kilometers deep. I really want you to take a moment to grasp the size of this feature. Imagine a crack running from New York City almost to Denver, Colorado, and you start to grasp the scale relative to the moon's size. It dwarfs Earth's Grand Canyon and is proportionally one of the largest canyon systems in the entire solar system, rivaled perhaps only by Valles Marineris on Mars. The existence of such an imposing feature on a seemingly simple icy moon begs the question, how did it form? Several theories have been proposed, but the leading hypothesis connects Ithaca Chasma to Tethys's internal evolution, suggesting that it may have formed early in the moon's geological history. As Tethys formed and subsequently cooled, any liquid water within its interior would have begun to freeze. Unlike most substances, water expands when it freezes. If Tethys once possessed a substantial subsurface ocean, or even just a partially liquid interior, the gradual solidification of this water would have caused the moon's volume to increase like an inflating balloon. This expansion would have placed immense stress on the rigid outer icy crust. Ithaca Chasma, according to this theory, is the result of the crust cracking and splitting apart under this relentless internal pressure. A global-scale stretch mark, signifying the moon freezing solid from the inside out. The sheer scale of the chasma suggests that Tethys might have expanded laterally by around 5% during this process, which is astonishing to consider. An entire moon swelling up until it literally began to burst. Other theories have considered links to the giant impact crater Odysseus, suggesting the shock waves might have fractured the opposite hemisphere. However, the chasma is thought to be older than the Odysseus basin, and detailed modelling suggests the expansion freezing model provides a better fit for the observed geology. Ithaca Chasma, therefore, isn't just a spectacular sight. It is a record of Tethys's thermal history, a dramatic indicator that this now frozen world may once have undergone growing pains on a cosmic scale. Surface temperatures on Tethys are incredibly low, averaging around 187 degrees Celsius, ensuring water ice remains brittle and stable against sublimation, except over very long geological timescales. It is cold enough there that the water ice on Tethys can often act like rock. Tethys lacks any detectable atmosphere, leaving its surface directly exposed to the harsh environments of space, micrometeoroid impacts, solar radiation, and charged particles within Saturn's magnetosphere. Only not all of those micrometeoroid impacts were micro. One was large enough that it nearly shattered frozen Tethys like a bullet through a snow globe. It is time to take a look at the Odysseus crater. If Ithaca Chasma speaks to internal forces, the Odysseus crater screams of external violence. Located on Tethys's leading hemisphere, Odysseus is the moon's largest impact basin, measuring approximately 450 kilometers across. That is more than 2/5 the diameter of Tethys itself. The impact responsible for this enormous feature is thought to have occurred between 400 million and 1 billion years ago. Judging by the size of the crater compared to its moon, if Tethys had been completely icy and hard like it is now, there is a significant chance the moon would have been broken into pieces. But it seems the impact occurred when Tethys's interior was still partially molten or slushy, allowing it to absorb and dissipate the impact energy more effectively than a completely solid, brittle body could have. An unlucky break that turned into a survival story. Interestingly, Odysseus is remarkably shallow for its diameter. Unlike the sharp, bowl-shaped craters we see on rocky bodies like our Moon or Mercury, Odysseus is relatively flat, its rim subdued, and its central peak complex largely collapsed. This is not how it would have looked immediately after the impact, and suggests a phenomenon known as viscous relaxation was at play over geological timescales. Even solid ice behaves somewhat like a very thick fluid, especially when topography is significant. The immense depression created by the impact and the uplifted rim would have slowly flowed and slumped under Tethys's own gravity, gradually smoothing out the crater's profile. The degree of relaxation observed in Odysseus provides further clues about the thermal state and composition of Tethys's crust at the time of the impact and in the eons since. This makes sense. Like a nuclear device suddenly detonating, such a large impact tends to release a massive amount of energy, and it would seem logical that not everything would remain icy. The impact likely resurfaced a significant portion of the surrounding terrain, either obliterating older craters or smothering them with its ejecta. So, Tethys has taken some hits over the years, both from within and without, but that is not all there is to this moon made of ice. Another notable discovery from Tethys was its unusual thermophysical properties, which amusingly tied it to a 1980s computer game character. In 2015, Cassini's composite infrared spectrometer made a series of observations of Tethys's daytime anti-Saturn hemisphere over a 9-hour time period. This produced data confirming an anomaly that had previously been identified in 2012, that the lower latitudes of Tethys's leading hemisphere appear cooler in the day and warmer at night compared to the surroundings. This area of Tethys also appeared darker in infrared and UV color ratio maps when compared to the rest of the leading hemisphere. Funnily enough, the pattern when mapped out made the moon look like a giant Pac-Man, which gave scientists a good chuckle. Proving their sense of humor, they gave this phenomenon the same name. Still, the Pac-Man heat map on Tethys, and a similar one on neighboring Mimas, needed an explanation. Tethys orbits Saturn at a distance of about 295,000 kilometers, making it the 5th largest moon in the Saturnian system. Its orbital period is short, just under 1.9 Earth days, and like most major Saturnian moons, it is tidally locked. Why does this matter? Well, this gravitational interaction ensures Tethys perpetually presents the same hemisphere towards Saturn, dividing its surface into a leading hemisphere, facing the direction of orbit, and a trailing hemisphere. This helps keep Pac-Man facing the same direction, which also brings us to its color. The leading hemisphere facing the direction of orbit appears to be between 10% to 15% brighter than the trailing hemisphere, and its near-infrared spectrum suggests that it has more pure water ice on its surface. This pattern is generally attributed to external factors. The leading hemisphere is the side that gets exposed the most to weathering by particles from Saturn's E-ring and Enceladus's plumes. This weathering effectively sandblasts material onto the surface of the leading hemisphere, which tends to consist of sub-micron-sized icy particles. Smaller water ice particles reflect more light than larger particles, therefore giving the leading hemisphere a higher albedo. The trailing hemisphere, conversely, is more heavily bombarded by energetic plasma particles trapped within Saturn's magnetosphere. This high-energy radiation can sputter surface molecules, break chemical bonds, and implant ions, processes collectively known as space weathering, which tend to darken and redden icy surfaces over time. Contamination by micrometeoroids carrying darker material could also play a role. In other words, we now think that Saturn's rings are to blame for feeding Pac-Man, as the differential bombardment from E-ring particles across the moon's leading hemispheres modifies the surface. This gives certain regions a higher thermal inertia, meaning they store and release heat more effectively than their surroundings, therefore creating the observed temperature differences. It is a pretty fun finding, one that makes you realize just how much these moons are shaped by their unique interactions with Saturn's rings. Tethys may lack the atmospheric complexity of Titan or the obvious present-day activity of Enceladus, but it is far from a boring, inert world. It is a body profoundly shaped by extreme events. Its story is writ large across its surface in the form of Ithaca Chasma and the Odysseus crater. It is also an incredible example of how worlds and moons are influenced by their wider neighborhoods. Tethys is icy, but the subtle variations in its surface texture and color hint at ongoing interactions with the Saturnian environment. Traveling around Saturn and its rings changes Tethys, and studying the two helps us better understand these dynamic interactions. Sadly, there are no new missions to Tethys currently planned. But Tethys has survived worse fates. It has been squeezed, it has been sandblasted with icy dust, and it has been struck from above with forces that could have shattered it. Tethys is a survivor. And although its crust is made of ice rather than rock, it is unapologetically hardy. It has weathered anything the universe has thrown its way so far, and will keep going strong. Titan greetings, everyone. We have finally arrived at the topic you have requested most frequently, Titan. And to be fair, I can completely understand the curiosity directed towards it. It is the only moon in the solar system with a substantial atmosphere. There is clear evidence of stable bodies of surface liquid on it, And best of all, mankind has visited it. So we are able to examine a wealth of real photos and video footage. I'm Alex Mccoan, and you are watching Astramm. Here is everything you could possibly want to know about Saturn's biggest moon, Titan. Let us start from the beginning and provide some context for this remarkable planet-like place. Titan is the sixth spherical moon from Saturn. Unlike Jupiter's 4 Galilean moons, in the Saturn system, Titan is in a class all by itself regarding size. The rest of Saturn's moons are comparatively small. To give some idea of how massive it is, Titan's diameter is 50% larger than Earth's moon, and it is 80% more massive. In fact, it is the second largest moon in the entire solar system, trailing only Jupiter's moon Ganymede. It actually appears slightly larger than Ganymede if you were to place them directly side by side, but this is an illusion caused by Titan's thick atmosphere, which extends its apparent diameter. Even so, Titan's physical diameter is still larger than the smallest planet, Mercury, although it is only 40% as massive. Since its density is quite low for its volume, its gravity is reasonably weak at only 0.14 Gs, or 1.35 meters per second squared, which is even less than the gravity on our moon. Due to Titan's low density, it is thought that its composition is roughly half water ice and half rocky material. Unlike other celestial objects of this size, it is believed Titan has a differentiated interior. This means it has distinct layers. Like many other large moons, one of those layers is thought to be a liquid ocean comprised of water and ammonia, situated under the moon's crust. This liquid ocean is comparable to Earth's magma layer situated between the core and the crust, and has been maintained in a liquid state due to heat, pressure, and to a certain degree, tidal forces. The existence of this liquid layer was proven more likely when Cassini, the spacecraft orbiting Saturn, discovered extremely low-frequency radio waves in Titan's atmosphere. Titan's surface is not known to be a good reflector of low-frequency radio waves, but a liquid interior would be. Another reason is that the surface features on the moon have shifted by up to 30 kilometers since Cassini started observations, which could imply that the surface is not rigidly attached to the core, but is rather floating on this liquid ocean layer. And while there is no evidence of life on Titan, scientists do speculate that the conditions would be right for there to be life in this subsurface ocean. Unfortunately, if there is life to be found on the surface or below, we will have to wait a while, as there are no currently planned missions to verify this possibility. Jupiter's Europa is a more likely candidate to be investigated for life in the foreseeable future. The differentiated interior of Titan does not produce a magnetic field. However, Titan is still quite protected from the solar wind, as 95% of its orbit around Saturn lies within Saturn's own magnetosphere. Titan orbits Saturn once every 15 days and 22 hours, and has a rather large orbital eccentricity, which means the orbit isn't perfectly circular. Its orbital plane is also at an angle, but that doesn't mean that Titan is likely a captured object. Rather, like Jupiter's Galilean moons, it is thought that Saturn also had several large moons in the past, but most of these were destroyed through massive collisions, leaving Titan as the lone victor. Saturn's medium-sized moons like Iapetus and Rhea are thought to be the remnants of this tumultuous beginning. Titan's day, like the day on our moon, is identical in length to its orbital period. This means Titan's rotation is tidally locked to Saturn, and it only ever shows one face to the planet. Not that visually it makes any difference. Titan's hazy atmosphere completely blocks the view of the surface from an outside perspective. On the other hand, you might just be able to see Saturn while standing on Titan, although the view would be significantly obscured by the haze. This tidal locking does mean, however, that if you were to stand on one spot on Titan facing the planet, Saturn would never appear to move in the sky. This leads us to one of the topics that truly sets Titan apart from the rest of the moons in the entire solar system: its substantial atmosphere. I remember the first time I ever saw a photo of Titan. I was truly blown away, as it never occurred to my younger self that a moon could even possess an atmosphere. I thought it must have been a new planet discovered recently. To me, what looks odd about the atmosphere is how far it stretches into space. When you see a picture of Earth, you see that the atmosphere has quite a tight fit around the planet. Titan, on the other hand, looks like it has a thick, puffy blanket all over it. There are a number of reasons for this. The first is that Titan is a lot smaller than Earth, but its atmosphere is 1.9 times more massive than Earth's, or 7.3 times more massive on a per surface area basis. The second reason is that Titan's gravity is a lot weaker than Earth's, meaning it doesn't pull the gases down as strongly, allowing them to expand outward. The mass of the atmosphere actually means the pressure at the surface is 1.45 atmospheres, or 45% more than the atmospheric surface pressure on Earth. Comparing the two, you can see the extent of how far Titan's atmosphere stretches into space. 600 kilometers high is only the limit of the mesosphere on Titan. Earth's mesosphere, on the other hand, stops at roughly 120 kilometers. Even at a distance of 995 kilometers, the Cassini spacecraft had to make adjustments to maintain a stable orbit against atmospheric drag when it made its closest approach. Like Venus, Titan is a super rotator, meaning its atmosphere rotates faster than the rotation of the planet itself. This can especially be seen at the poles. Each pole has a polar vortex that rotates once every 9 hours, compared to the moon's solid body rotation of 16 days. The vortexes on each pole seem to be like permanent hurricanes. So, what does the atmosphere consist of, and why is it orange in color? Well, the atmosphere is 98.4% nitrogen, the remainder being mainly methane and small amounts of hydrogen. There are also trace amounts of complex hydrocarbons formed from the breakup of methane in the upper atmosphere due to ultraviolet light. It is these hydrocarbons that are thought to give Titan its signature orange hue. This constant breakup of methane into hydrocarbons implies that the moon should have run out of methane within 50 million years. A very short space of time compared to the age of the solar system. This means there must be a source that replenishes the methane. The most likely candidate is cryovolcanoes, although biological life has not been theoretically ruled out as a source. The methane in the atmosphere creates a greenhouse effect, without which the temperature on Titan would be significantly lower. Conversely, however, the haze also reflects a lot of the sunlight back into space, creating an anti-greenhouse effect, which cancels out some of the potential warming from the methane. While Titan's upper atmosphere gets roughly 1% of the sunlight, Earth does due to the distance from the sun, this reflection means the surface of Titan only gets about 0.1% in the end. The Huygens team liken the difficulty of taking photos at this light level to taking pictures of an asphalt parking lot at dusk. All these things combined mean that while it would be dim, a human would only need an oxygen mask and extremely warm clothing to be comfortable while standing on the surface of Titan, thanks to the pressure. It really is cold on Titan, 180 degrees centigrade on average. This means any water on Titan remains rock hard solid and doesn't ever melt, evaporate, or sublime. Then, why are there sometimes clouds on Titan? These are not water ice clouds, but rather methane clouds, which means yes, it can rain methane on Titan. In fact, the temperature on Titan is just right for methane to exist as a liquid. Methane freezes at 182.5 degrees centigrade and boils at 161.5 degrees centigrade. The temperature combined with the surface pressure got scientists very excited at the prospect of there being hydrocarbon lakes or seas on the surface of Titan, similar to water lakes and seas on Earth. If there really were lakes on this moon, it would be the first time this had ever been observed outside of Earth. This was actually one of the main driving forces behind the Cassini-Huygens mission, to see what existed under that thick atmosphere. The Huygens probe, named after the astronomer who discovered Titan in 1655, was designed to enter Titan's atmosphere and land on the surface. The possibility of landing on an ocean was taken into account during its design process. As the probe descended, its parachute was deployed, and after an almost 3-hour journey, it finally rested on the solid surface of Titan. Sadly, it wasn't able to see any lakes directly, but what it did see confirmed that methane lakes once existed, as Huygens landed on what appeared to be a dried up lake bed. The stones visible in the surface photos are rounded, much like pebbles found in a river or a lake on Earth, smoothed by flowing liquid. From the perspective of space, Cassini was able to confirm that methane lakes are indeed found on Titan today. Near the South Pole, Cassini observed an area which was later confirmed to be a lake called Ontario Lacus. It is 20% smaller than its North American namesake, Lake Ontario, but at 15,000 square kilometers, it is still substantial. On one side of the lake, you can see a smooth shoreline eroded by waves. On the west side, you can see the first evidence of a river and delta on Titan, meaning that liquid hydrocarbons flow down from higher planes to the lake, leaving delta deposits in much the same process found on Earth. Ontario Lacus is extremely shallow, estimated to be between 40 centimeters and 3 meters deep on average, with the deepest point likely just over 7 meters. As Cassini's radar mapped this lake, it found that the lake did not have waves bigger than 3 millimeters, meaning the surface would appear like a sheet of glass or a mirror. This doesn't mean there can't be bigger waves, unless this liquid is particularly viscous, but the likelihood is that it was simply not a windy day when the observations were taken. The atmospheric density and gravity on Titan should theoretically allow for waves larger than those on Earth. As the North Pole of the Moon began to come out of a 15-year winter, another lake was discovered, Jingpo Lacus. As Cassini was passing by the Moon, sunlight was reflected off the surface of Jingpo Lacus like a mirror directly into the view of Cassini. Upon further observation, Cassini was able to detect further evidence of moving liquid on Titan, as seen by rivers flowing into this lake. The second largest lake on Titan to be discovered is Ligeia Mare. Found in the North Pole region, it is bigger than Lake Superior on Earth, with a surface area of 126,000 square kilometers. While parts of this lake are reasonably shallow, the average depth is much greater than Ontario Lacus at 50 meters, and some parts could reach depths of over 200 meters. Plenty of rivers can be seen flowing into the lake, and there are large islands found around this area. A particularly curious observation Cassini made, dubbed the Magic Island, involves the appearance and subsequent disappearance of what looks like an island feature. Although scientists are unsure exactly what happened here, theories suggest it could be silt suspended in the lake, rising bubbles, or subsurface ice floating to the surface as the lake warmed during the moon's spring. It remains a very curious phenomenon. The largest lake on Titan, at 400,000 square kilometers, is Kraken Mare. As you can see, the lake is split into two main parts, separated by a narrow channel quite similar to Earth's Strait of Gibraltar. Its nickname is the Throat of the Kraken. Because of tidal forces and the immense size of the lake, it is thought the tide changes by about 1 meter, and so this strait may experience strong currents and even whirlpools. Kraken Mare is also quite deep, though likely not deeper than roughly 170 meters in most places. So, we know about the lakes on Titan now, but what other interesting surface features might it have? Plenty, actually. Titan's surface is quite young, effectively as young as 100 million years old in places, which means its surface must be geologically active. Some scientists believe the dirty ice crust is substantially rigid, although there is evidence to suggest tectonic activity, possibly caused by tidal forces with Saturn. The main factor of a renewed surface, however, is likely the same mechanism that produces methane in the atmosphere: cryovolcanoes. This is fascinating geology. You know how magma on Earth is extremely hot rock, and when it comes out of the ground, it freezes into solid rock? Titan has the same process, except its magma is a mixture of water and ammonia. When it erupts from cryovolcanoes and spills over the land, it freezes to renew the surface. Because a water and ammonia blend is much less viscous than molten rock, it flows further than lava on Earth. This means mountains are flatter and will never reach the towering heights of volcanoes on Earth. While it is hard to confirm specific cryovolcanoes on Titan, due to the obstruction caused by the atmosphere, the most likely candidate is Sotra Patera, found in the southern hemisphere. In some images, the height has been exaggerated by a factor of 10 to make it visible. but it gives a good idea of the size of the dome and the 1.7 kilometer deep pit, the largest known on Titan. The force necessary for this to erupt would have been incredible, and while it doesn't appear to be active right now, it is being actively monitored. The fact that lava on Titan is a mix of water and other minerals means the surface could be compared to dirty ice. Because we know the Huygens probe bounced and wobbled in a specific way as it landed, we have a rough idea of the surface consistency. Scientists have referred to it as having the texture of soft, damp sand. Another theory is that it is like snow with a thin, crunchy crust on top. Imagine walking on frozen snow. If you're careful, you can stay on top, but if you stomp too hard, you sink in deeply. Titan's surface is believed to be something like this. Titan's highest mountains come in the form of ridge belts, somewhat like the Rockies in America. These ridge belts could also be a form of cryovolcanism or tectonics. The largest mountain on Titan can be found in one of these ranges, known as Mithrim Montes, and stands 3,237 meters high. Interestingly, mountains this tall are thought to be topped with methane snow. What are also found on Titan are many gorges, valleys, and dunes. Using infrared cameras to see the surface from space, large patches of dark terrain are prominent. Originally, these dark patches were thought to be seas until the Huygens probe landed on one of those areas, known as Shangri-La. They could well have been seas in the past, but now they are plains of dark mineral deposits similar to the Namib Desert on Earth, appearing as windswept dunes in some places. Overall, Titan can be compared to Earth in many ways. Scientists think that Titan shows signs of what early Earth could have been like, only much colder. It is fair to say that Titan is remarkably interesting, and I can only hope it gets its own dedicated orbiter or lander mission one day. Cassini has done a great job, but it was never solely a Titan orbiter, and its mission has concluded. What I would find extremely fascinating is to explore more of its surface. Hopefully, it won't be long until a mission to do exactly that is approved. Enceladus stands out as arguably one of the most captivating objects within our solar neighborhood. Yet, strictly speaking, it is only the 6th largest moon of Saturn, and in natural light, it appears quite unassuming. However, there is a great deal more to Enceladus than meets the eye. It is an active, dynamic, icy world with jets of water vapor pouring out from its southern hemisphere. Thanks to the remarkable Cassini mission, we have studied and observed Enceladus in exquisite detail and perhaps know more about it than some of the closer and larger Jovian moons. However, although we have seen a lot from the outside, it is the inside of the moon that still holds so many mysteries. Let us first discuss where Enceladus fits into our solar system. Enceladus is currently Saturn's 14th closest moon. I say currently because Saturn has some tiny moonlets hidden in its rings that may or may not be formally classified as moons in the future. It is the second closest major moon, however, second only to Mimas. That means its orbit takes it just outside of Saturn's major rings. Its orbit follows the plane of the rings very precisely, and it takes only 33 hours to orbit Saturn once. Interestingly, it is in a 2.1 orbital resonance with Dione, Saturn's 4th closest major moon. In other words, Enceladus orbits twice around Saturn in the exact time it takes Dione to orbit once. This orbital resonance is believed to prevent Enceladus's orbit from ever becoming perfectly circular, which forces Enceladus to undergo tidal deformation. This is significant as these tidal forces generate friction and heat up Enceladus's core. As far as we can tell, Enceladus's surface is predominantly made of clean water ice, certainly with little to no rock or contaminants exposed. Because Saturn is situated so far away from the Sun, the outer layer of water on Enceladus has frozen solid. Enceladus is essentially a frozen ocean world, a giant ball of water ice. Because it is free from other materials on the surface, the Moon is one of the whitest objects in the solar system, boasting a bond albedo of 0.81, which is practically as reflective as fresh snow. As such, it is one of the coldest satellites of Saturn, with a noon temperature of 200 degrees Celsius, as the white color reflects a large percentage of the meager sunlight reaching it back into space. However, about 30 to 40 kilometers beneath the surface, pressures start building, and heat energy generated from the tidal deformation of its orbit has increased the temperature of the water ice to the point where water at this depth can exist in liquid form. It could well be that there is an entire mantle or a global ocean of water that the ice crust is resting upon, very much like the magma mantle that our rocky crust on Earth rests upon. At the very least, scientists expect there to be a huge pocket of water under the moon's south pole. How do we know this? The most obvious indication are the huge plumes of water being ejected from cracks in the crust, a phenomenon referred to as cryovolcanism. These jets are incredibly active, consistently blasting around 250 kilograms of water into space every single second at speeds exceeding 2,000 kilometers per hour. This is powerful enough that most of the water vapor particles escape Enceladus's weak gravity, and they end up in orbit around Saturn, forming Saturn's E-ring. This ring is very diffuse, so it isn't really visible unless it is backlit by the sun. From this angle, the light shining through the water particles makes the ring appear exceptionally blue. In fact, this ring is considered the bluest object in the solar system, even more so than the planet Neptune, due to the ring's uniformity. The E-ring is Saturn's second outermost ring, and it is 2,000 kilometers wide. Its shape is heavily influenced by the orbit of Enceladus. The plumes create tendril shapes in the rings as more material erupts. However, these sections tend to smooth off as Enceladus moves further along its orbit. During the course of the Cassini mission, the spacecraft was able to fly directly through these plumes to detect the substances being ejected. Cassini wasn't designed with this specific task in mind. Scientists didn't know about the plumes until Cassini arrived. However, Cassini was equipped with an instrument called the Cosmic Dust Analyzer, designed to detect what the tiny dust grains in orbit around Saturn are made of, and it was able to use this for Enceladus's plumes too. Since it wasn't specifically designed for this, it might not have given us the full picture. But while water was the predominant substance detected, amino acids, carbon dioxide, nitrogen, and methane were also found. Amino acids are significant as they are the building blocks of life and can be found around thermal vents at the bottom of Earth's oceans. Does this mean Enceladus has thermal vents of its own? And if so, do they host ecosystems of life around them? While evidence for an underground ocean is abundant, scientists still aren't completely sure about Enceladus's internal structure. At some points in the past, scientists believed that Enceladus was water all the way through. However, data from Cassini suggests that Enceladus's mass is in fact greater than previously thought, meaning it must have some amounts of iron or silicate material in its core. Scientists are starting to lean towards the theory that the internal structure is differentiated, meaning it has defined layers. An object of this size really doesn't have to be differentiated. In fact, it is so small, at only about 500 kilometers across, that it is right on the borderline of being in hydrostatic equilibrium, or being rounded by its own gravity. There are a number of objects out there of similar or smaller sizes that are not in hydrostatic equilibrium, like Neptune's moon Proteus. In any case, assuming it does have a differentiated interior, this core is likely to be predominantly rocky. This is important, as thermal vents in Enceladus's water ocean would have to stem from a rocky core. A rocky ocean floor would also provide nutrients and minerals essential for what we believe life would need to form and evolve. Thermal activity clearly does exist due to the way Enceladus generates plumes in the first place, and the amino acids detected in the plumes further suggest a rocky core interaction. As Cassini passed over Enceladus, it also mapped out the thermal emissions from the moon. It turned out that the jets line up with what has come to be known as Enceladus's tiger stripes. These are large depressions roughly 130 kilometers long, 2 kilometers wide, and 500 meters deep. It is believed that these are tectonic fractures in the moon's icy crust. What is really interesting about the surface features of Enceladus is that there are virtually no impact craters at all over the southern hemisphere, and not many anywhere else. This implies that Enceladus' surface is very young. While it does have a thin atmosphere made up from the ejected water from the plumes, this isn't nearly enough to burn up asteroids before they hit. Some water from the plumes obviously settles again on the surface, which smooths it off over time, acting like fresh snow. This is another reason why Enceladus is so round for such a small celestial body. In fact, apart from the tectonic fractures and few craters, Enceladus' topographical variation is quite minimal. There are no mountain ranges to speak of, although there is what you might call rough terrain around the South Pole if you zoom in far enough. High-resolution imagery reveals a landscape that appears like a giant glacier. It is interesting to note that even in this small view, there are some smooth sections of ice alongside jagged regions. Over the North Pole, the clear difference is the number of craters present. While there are tectonic fractures here too, there are no plumes on this side of the moon. So the surface here is clearly a lot older than around the South Pole, which is why it has retained a more cratered appearance. As Cassini flew through the plumes around the South Pole, it also took the opportunity to image the surface closely around the tiger stripes. The surface here is pretty incredible, unlike anything you would have seen on Earth. It is as if the surface has been folded, squashed, and shifted around, leaving these remarkable fracture lines and formations in the surface ice. The fact that Cassini was able to get so close to Enceladus is a feat in itself. It is fantastic that we can have such a close-up view of something so distant. Unfortunately, since the Cassini mission has ended, we no longer have anything in orbit around Saturn that can study Enceladus further. There have been plenty of mission proposals in the past, but all of them were cancelled before they came to fruition. What would be incredible is a probe that could either make its way into Enceladus' ocean somehow, or at the very least, search the plumes specifically for signs of biological life. There is already a mission called Dragonfly going to the nearby moon of Titan. However, this won't have anything to do with Enceladus. Although a couple of mission proposals are currently under review, we are unfortunately still a couple of decades away from a return visit, which is a shame because who knows what secrets lie in wait under that crust.